Hello everyone, welcome back to my channel. Today we would be discussing the questions of IBDP HL Chemistry Paper 2 of Time Zone 2 of year 2021. So let's start with the first question. We have this question where limestone can be converted into a variety of useful commercial products through lime cycle, and the lime cycle is given here. So the first question says that calcium carbonate can be heated to produce calcium oxide and carbon dioxide. So we need to find the volume of carbon dioxide produced at STP when 555 grams of calcium carbonate decomposes. But first we need to find the moles of calcium carbonate. To find the moles of calcium carbonate, we have to divide given mass with the molar mass. Molar mass of calcium carbonate will be equal to 100 grams. Okay, so we get 5.55 at the moles of calcium carbonate. Now, as the stoichiometry is 1:1, so 1 mole of calcium carbonate will give rise to 1 mole of CO2. So moles of CO2 in this case will be equal to 5.55. So now the volume of CO2 will be moles times the molar volume. Moles is 5.55, molar volume is 22.7. So finally we get the answer as 125.99 decimeter cube. Okay. Now, why do we need to use section 2 and 6 of the data booklet? I'll just explain it to you. From section 2, we will basically get the molar volume, that is 22.7, okay, for an ideal gas at STP. And from section 6 is basically the periodic table, and using section 6 we have to calculate the molar mass of CaCO3. So coming to the next question, we have the thermodynamic data for the decomposition of calcium carbonate. So we have like the substances in their delta HF, that is the heat of their formation, and their entropy. Okay, the CaCO3 has -1207, 93, and similarly we have values for CaO and CO2. So we need to find the enthalpy change of reaction for the decomposition of calcium carbonate. So delta S, that is the enthalpy of the reaction, is summation of delta HF of products minus summation of delta HF of reaction. This is the standard equation. So we have products as CO2 and CaO. So minus 635 and minus 393.5. This is the net summation of the enthalpy of enthalpy of formation of products. And we need to subtract the enthalpy of formation of the reactants. And the reactant is calcium carbonate. We get this from this equation here. So for calcium carbonate, it's -1207. So plugging the value in this equation, we get delta HS 178.5 kilojoule per mole. Okay. Now we need to find the enthalpy change for the reaction. So we have to multiply delta H with the total number of moles of the products. Okay, this is the delta H total. Okay, the total enthalpy of this reaction, or how much heat will be generated, or this heat has to be absorbed. In this case, it is absorbed because delta H is positive. So yeah, so we need to multiply delta, that is 178.5, with the moles of CaCO3, and we will get 990.68 kilojoules as our final answer. Now, coming to the next part, we need to find the entropy change in Joule Kelvin inverse of the decomposition of calcium carbonate. So delta S similarly will be summation of delta SF of products and we need to subtract the summation of delta SF of reactants. Okay, products are CaO and CO2. So 40 plus 214 will be the summation of delta SF of products, and our reactants is just CaCO3. The summation delta SF of reactants will be 93. Plugging them in this equation, we get delta S as 163 Joule Kelvin inverse mole inverse. Now to find the total entropy, we have to multiply this delta S with the total number of moles. So 163 times 5.55, we get 904.65 Joule Kelvin inverse. And that's the final answer to this part. The next question is, determine the temperature in Kelvin at which the decomposition of calcium carbonate becomes spontaneous using B1, B2 for section 1 of the data booklet. Now we don't need this data because we already know the correct answers of B1, B2. So let's try to solve this question. So we need to find the temperature. So the reaction will be just spontaneous when your delta G, or the Gibbs free energy, becomes 0. If your Gibbs free energy delta G is positive, then the reaction is non-spontaneous. If your delta G is negative, it becomes spontaneous. So delta G equals 0 is the cutoff value, and you can say at this temperature your reaction just becomes spontaneous. So plugging, so we know the equation is delta G equals delta H minus T delta S, and we can use section 1 again. If you just check here, I haven't put it I guess here, but section 1 gives you this formula, that is delta G equals delta H minus T delta S. Okay, so yeah, so if we put delta G equals 0, so we get 0 equals delta H minus T delta S. So temperature becomes delta H divided by delta S. Okay, so delta H is 178.5. Now delta, this is kilojoule and this is joules. Okay, so we need to multiply this delta H with 1000 to convert it to joules per mole. Okay, so 178.5 times 10 cube divided by 163. 163 was the entropy of the reaction. So we finally end up with 1095.1 Kelvin. This is the answer to this part of the question. Now we need to we'll be going to part 4. Here we have to set the energy profile for the decomposition of calcium carbonate based on your answer to B1 and labeling the axis and activation energy. So the reaction coordinates, okay, or how much the reaction is proceeding, it will be plotted on the x-axis, while the energy will be plotted on the y-axis. Now we have to show the activation energy in this graph, and we need to draw the graph with reference to part B1. So in B1, we saw that our delta H of this reaction is positive. So our reaction is endothermic. And for endothermic, obviously, we know that the energy of products is more than the energy of reactants. So products will be here, reactants will be here. Now, obviously, what happens is the reaction will proceed after, the regular energy profile of any reaction will specifically look like this. So the reaction only proceeds forward if it crosses the activation energy. And the energy difference between reactants and the maximum energy required, this becomes your activation energy. That's all to part 4. Let's go to part 5. See how adding a catalyst to this reaction would impact the enthalpy change of the reaction, delta H, and the activation energy. Now, what happens is when we add a catalyst to a reaction, this catalyst doesn't interfere with the reaction. Okay, so catalyst itself remains unchanged. But two of the the catalyst remains unchanged, but in the reaction, the activation energy changes. So what happens is the catalyst provides an alternate pathway for the reaction. Okay, so that's for that reason your activation energy will decrease. Okay, because if the activation energy increases, then obviously there would be no use of that catalyst. We want to decrease the activation energy so that more and more of our reactors can get converted to products. And delta H, this doesn't change. Okay, because activation energy will lower this EA value, but the difference between products and reactants, this is delta H, this will remain constant. Now let's go to part C. The second step of lime cycle produces calcium hydroxide, that is CaOH whole twice. We need to find the reaction between calcium hydroxide with HCl. So obviously it's an acid-base reaction. This is the base, this is the acid. So our products would be salt and water. This is salt, this is water. So the CaOH whole twice plus HCl gives us CaCl2 and H2O. Now we have to balance it. On balancing, you would just see that there would be 2 in front of HCl and 2 in front of H2O. And that's all about it. Next is we have to determine the volume of 0.015 mole per dm cube of calcium hydroxide solution that is needed to neutralize 35 centimeter cube of 0.025 moles per dm cube HCl. Now see, firstly, let's calculate the moles of HCl. So moles of HCl is your molarity or the concentration times volume. Volume is in centimeter cube, but we need to convert the centimeter cube to decimeter cube. So I multiplied it with 10 to the power minus 3. So this becomes the moles of HCl. Okay. Now we have to check this equation. Okay. The stoichiometric ratio between HCl and CaOH whole twice is 2. Okay. So for, to neutralize each mole of CaOH whole twice, I would need 2 moles of HCl. So I can write the stoichiometric ratio, moles of CaOH whole twice divided by moles of HCl. This will become 1 by 2. So moles of CaOH whole twice would be moles of HCl by 2. So that's what I have written here. So from here we can calculate the moles of CaOH whole twice. Now we got the moles of CaOH whole twice. Now we need to find the volume that is required. So this is the formula for concentration, moles per volume. So volume becomes volume becomes moles divided by concentration. So upon further calculation, we find that volume is 0.0292 dm cube, and we have to keep our answers in dm cube as instructed in the question. The next one, saturated calcium hydroxide is used to test carbon dioxide. Calculate pH of 2.33 times 10 to the power minus 2 mole per dm cube solution of calcium hydroxide, which is a strong base. Now, they have specifically told us to consider calcium hydroxide as a strong base. So what happens is each mole of carbon dioxide will give rise to 2 moles of OH minus ions. So our concentration of OH minus will be double of that of CaOH whole twice. Okay, so if there's the concentration of CaOH whole twice, OH minus concentration will be CaOH whole times 2, and we get 4.66 times 10 to the power minus 2 as the concentration of OH minus. Now we can find POH. POH is minus of log of OH minus. Okay, and if you plug this value here in OH, you will get the POH value as 1.33. Now pH, we know pH, the formula of pH is 14 minus POH. The 14 minus 1.33, it becomes 12.67, which makes sense because CaOH whole twice is a strong base. So our value of pH should be somewhere close to 14 if we are using a strong base. So yeah, this is the correct answer to this question. Moving on to part D. So here, calcium hydroxide reacts with carbon dioxide to reform calcium carbonate. Okay, and water is our byproduct. We have to determine the mass of calcium carbonate produced by reacting 2.4 by dm cube of 2.33 times 10 to the power minus 2 mole per dm cube of calcium hydroxide with 0.75 dm cube of CO2 at STP. Okay, so see, calcium hydroxide and CO2 are in 1:1 ratio. Okay, so between both of them, the one with the lesser amount of moles will be our limiting reagent. So let's try to find the moles of calcium hydroxide. This is the volume, this is the concentration. So volume times concentration will give us the moles of calcium hydroxide. Moles of CO2 would be 0.75 divided by the molar volume. That would be 3.3 times 10 to the power minus 2. On comparing both of them, we obviously CO2 has a lesser value. So CO2 will be our limiting reagent. Okay, and we will use the limiting reagent as the basis of our calculation. So using the moles of CO2, obviously these two are in 1:1 ratio. So moles of CO2 will be equal to moles of calcium carbonate. That is 3.3 times 10 to the power minus 2. Now the mass of calcium carbonate is moles times the molar mass. Molar mass of calcium carbonate is 100, which I've written here. So finally we get 3.30 grams as our final answer. In the next problem, we have 2.85 grams of calcium carbonate that was collected in experiment in the D part 1. Calculate the percentage yield. So this one is pretty simple. Percentage yield is basically your experimental yield divided by the theoretical yield times 100. Experimental yield is the amount that you obtain via your experiment. Theoretical yield is the amount that you obtain via your calculations. So we know from the previous question theoretical yield is 3.30 grams because we obtained it by our numerical calculations, and the experimental yield will always be given in the question. So it's given 2.85 here. So 2.85 divided by 3.3 times 100. This should be your percentage yield. Upon calculation, you will find it as 86.36%. So yeah, that's all about part D. Now we'll move on to part E. Now we have to outline one calcium compound in the lime cycle that can reduce a problem caused by acid deposition. In the lime cycle, to reduce problems by acid deposition, obviously we need to use a base. So calcium hydroxide is a base, it's a strong base. And what happens is due to acid rain, fertile soil becomes acidic. And when the fertile soil becomes acidic, what happens is it becomes unfit for cultivation. So you can't grow crops on acidic soil. To fix this problem, what we can do is we can add calcium hydroxide to the soil and make the soil neutral again, or a little basic, which is good for the plants. And again, we can start growing crops on the land. Now, moving on to the next question. In question 2 is given that the properties of element can be predicted from their position in the periodic table. The first part A, part 1, explain why Si has a smaller atomic radius than aluminium. So to solve this question, we actually need to look at the periodic table. So we know that Si is situated just at the right of aluminium. Okay, so what happens exactly here? Both of them are in the same period. Okay, so they will have the same number of shells. But Si having a greater atomic number, what happens is it will have more protons as compared to aluminium. Okay. Now, what happens is, as Si has more protons, but the shell number is equal in both Al and Si, so these protons will pull the electrons towards the nucleus with a greater intensity. Okay, so yeah, I've written that exactly here. Electrons are pulled towards the nucleus with a greater intensity in silicon as compared to aluminium. So that's the reason why Si has a smaller atomic radii as compared to aluminium. Moving on to part 2 of this question. Explain why first ionization energy in sulfur is lower than that of phosphorus. So to solve ionization enthalpy questions, I always prefer to write the electronic configuration because most of the answer will probably be hidden there. So what happens is phosphorus has 3 electrons in its 3p subshell. Okay, and all of them will be obviously unpaired because 3 electrons in 3p subshell. So we will have 1, 1, 1 here. So while sulfur has 4 electrons in its 3p subshell, 4 electrons means one of the orbitals will be paired, the rest 2 will be unpaired. Okay. Now what happens is this electronic configuration of phosphorus is actually stable because it has kind of a symmetry. Okay. While this electronic configuration of sulfur is a little unstable as compared to the electronic configuration of phosphorus. So what happens is if we remove one electron from the 3p subshell of sulfur, we will gain the electronic configuration of phosphorus, right? So yeah. So what happens if we remove one electron, the sulfur atom will become more stable. Okay. That is exactly the reason. Okay, and that is why sulfur has a lower ionization energy than that of phosphorus. Obviously, stable system will have a greater ionization energy. So yeah, that's the answer to this question. The next question is we have to write the condensed electronic configuration of Cr and Cr3+. The chromium from this periodic table, you know, it's at 24. So 24 means here you have argon. This is the closest noble gas. So Ar 4s1 3d5. Now for Cr3+, what we need to do is always remove electrons from the S subshell first and then the D subshell. So we'll remove 1 electron from S subshell and 2 electrons from D subshell. We'll be left with Ar 3d3, which is the electronic configuration of Cr3+. In the next part, we have to describe metallic bonding and how it contributes to electrical conductivity. Okay, so what happens is metallic bonding is basically an electrostatic force of attraction that is between the localized electrons and positively charged metal ions. So what happens is each electron is attracted by all the positive ions in the metallic structure. Okay, and this is the reason how the lattice is held together. Now another thing is these delocalized electrons are free to move about in the lattice or the metallic structure. Okay, so what happens if you put a potential difference or if you put a voltage about this metallic structure, these electrons can move in a specific direction, and that's what we call as conducting of electricity. And that's the answer to this question. Now, moving on to part 3, we have to deduce giving a reason which complex CrCN6 3- or CrOH whole 6 3- absorbs higher energy light, and we have to use section 15 of data booklet. So here section 15 gives us a spectrochemical series, which gives us basically the energy difference between the two sets of d orbitals after splitting, like the energy difference between Eg and the T2g orbitals. From here, we see that in Cn-, the energy between T2, between the splitted orbitals is much more. This is the energy. This energy is much more for Cn- as compared to OH-. Okay, so as this energy gap is much higher, obviously it requires a higher energy. Okay, and that's the reason why CrCN6 or the Cn- ion will absorb higher energy light. Okay, so the Cn- ligand has a higher splitting of its d orbitals as compared to OH, hence CrCN6 3- will absorb higher energy light. That's the answer to this question. The next part, CrOH whole 6 3- forms a green solution. Estimate a wavelength of light absorbed by this complex using section 17 of data booklet. So this is section 17. So see, green light is visible. Okay, if green light is visible, that means it has absorbed the light which is opposite to that of green of this color wheel. So it has absorbed red light. Okay, and the wavelength of red light is in between 700 and 647. So any wavelength value in between 700 and 647 will be true. Okay, so your answer can be anywhere between 647 to 700. Maybe you can choose like around 670 or something, which is in between. Now we have to deduce the Lewis structure and molecular geometry of sulfur tetrafluoride, which is SF4, and sulfur dichloride, that is SCl2. Now I'll clearly explain the method how to solve these questions, and they contain actually high marks, so we should focus a little bit time on this question. So firstly, SF4, the central atom is sulfur, and in sulfur dichloride, the central atom is again sulfur. So sulfur has 6 valence electrons. Okay, and it will make 4 bonds with fluorine. Okay, so 4 bonds, 4 covalent bonds with fluorine means sulfur will donate 1 electron to each of the fluorine. Okay, so after these 4 bonds, total number of electrons left in the valence shell will be equal to 2. So that means it has 1 lone pair and 4 bond pairs. Okay, so 4 bond and 1 lone pair. So the Lewis structure will kind of look like this. Okay, 4 bonds and 1 lone pair. We'll also have to show the lone pairs of fluorine. Fluorine has a total of 7 electrons. It makes 1 bond, so it has 3 lone pairs. Okay, now about the molecular geometry. So total it has 5 electron pairs, right? 4 bond pairs and 1 lone pair. For 5 electron pairs, our hybridization is sp3d. Okay, you can add up s, 3p and 1d, it becomes 5. So sp3d will be our hybridization. Among sp3d, we have to look for the molecular geometry of 4 bonds and 1 lone pair. And that is basically the seesaw geometry. There is a list in all the books. You can follow that and you will find that the molecular geometry is seesaw. So molecular geometry is seesaw for this part. Now coming to SCl2. Again, for SCl2, valence electrons for sulfur will be 6. Total valence electron after bonding, there will be 2 bonds. So 2 electrons will be donated. So 6 minus 2, that will be 4. So total lone pair will be 4 divided by 2, that is 2. And total bonds will be 2. So we can draw the structure of SCl2, 2 bond pairs and 2 lone pairs. We also have to draw the lone pairs of chlorine. Chlorine being a halogen, after forming 1 bond, it will have 3 lone pairs in its valence shell. Now it has 4 electron pairs, so the hybridization will be sp3. Okay, s and 3p. So sp3, the molecular structure of sp3 with 2 bond pair and 2 lone pair is the bent molecular structure, and that would be our answer here. It's bent. So that's all for this part C. Moving on to part D. We have to suggest giving reasons the relative volatility of SCl2 and H2O. Okay. So SCl2 will be more volatile as compared to H2O. Okay, this is the main comparison. Now coming to the reasoning. Now this reasoning, I find this reasoning the best, so we'll go with it. So what happens is H2O can form a network of intermolecular hydrogen bond with other H2O molecules. Okay, while SCl2 can only form dipole-dipole interaction because SCl2 is a dipole. Okay, so it can only form dipole-dipole interaction. Now we know that hydrogen bonds are much stronger as compared to dipole-dipole interactions. Okay, so it would be easier to heat up SCl2 and convert it into a gas. Okay, and that's why SCl2 is more volatile as compared to H2O. And that's all for this part D. Moving on to question number 3. Here, it's written oxidation reduction reaction can have a variety of commercial uses. So they are basically talking about cells. So a student decides to build a voltaic cell consisting of aluminium electrode and a tin electrode and the solution of aluminium nitrate and tin nitrate. So voltaic cell, that is an electrochemical cell. So what happens is this cell will generate electricity. Okay, so electron flow has been represented by this diagram and we have to just label this diagram. So this thing, obviously it's a voltmeter, okay, or the ammeter, whatever you say, that's correct. This is the salt bridge. So up to this, these two are pretty known to everyone. This is obviously common for any of the voltaic cells. Now comes the main part. Okay, so electrons are generated at this end, okay, and electrons are received at this end. The end where electrons are generated, that end actually faces oxidation, and the end that receives electrons are reduced. So this is the oxidized end, okay, and this is the reduced end. So we know this term anox and red cat, okay, which I have told lots of times during our lectures. So at the anode there is oxidation, at the cathode there is reduction. So this part is the anode, this part is the cathode. Now we have to identify which will be at the anode and which will be at the cathode. And for this, you have to use section 25. Section 25, you see Al is much higher as compared to Sn. Okay, so that's the reason Al will get oxidized and Sn will get reduced. Okay, so Al will be at the anox side. So here you will have Al and you will have Sn at the cathode side. So obviously Al, it will come with the solution containing the aluminium salt. That is AlNO3 whole twice will be here and SnNO3 whole twice will be here. And that's all about this question. Now in the next part, you have to write the overall expected chemical reaction. So after you write, after you balance the half reactions will be Sn2 plus 2 electrons giving you Sn, and you will have another Al gives you Al3 plus 3 electrons. Okay, now you have to multiply this thing with 3 and this thing with 2 and add these two together, and you will finally end with this equation because you have to remove the electrons in both of these half reactions. Okay, so yeah, finally we end this 3 Sn2 plus twice Al gives you twice Al3 plus and thrice Sn solid. Now you have to find the cell potential using section 24. So E naught of this cell is E naught cathode minus E naught anode. E naught cathode, you see here, cathode is minus 0.14 and you will have E naught anode as minus 1.66. Okay, so minus 0.14 negative of negative 1.66 gives you 1.52 volts, which is the correct answer to this question. Next one, we have to calculate Gibbs free energy using section 1. The section 1 basically gives you this formula, delta G is minus NF E naught. Okay, so just plug in the value. N is the total number of electrons that you cancelled in the balanced reaction. Okay, so in this case, what happens is, if you remember, we had Sn2 plus, plus 2 electrons gives you Sn, but we multiplied this equation with 3. So total, if you multiply with 3, this becomes 6 electrons. So N is 6 basically in this case. Okay, this is the total number of electrons that you cancelled on both sides for a balanced chemical reaction. So N is 6. F, we need to get this value of F. It's given in section 20, section 2. Is 9.65 to 10 to the power 4. And we have E naught value of 1.52 joules. On multiplying all of this, we have 880080 joules. So you can just divide it by 1000 and we will get delta G value as negative 880.08 kilojoules. Okay, delta G is negative. That means this cell reaction is spontaneous and the cell exists. Okay, so that's all about question 3. Let's move on to question 4. So organic chemistry can be used to synthesize a variety of products. So this is the organic chemistry question. So several compounds can be synthesized from butene. Draw the structure of final product for each of the chemical reactions. So this is butene, butene. Okay. If you put H2 in platinum, what happens is it's hydrogen addition. Butene gets converted to butane. So double bond gets removed and you attach 2 hydrogens here. So as a result, it looks something like this. Okay. Now next one is L plus H2 and H plus. Okay. H2 and H plus is basically the water addition reaction. Now as this molecule is symmetric in nature, we don't have to apply our Marconi-Curve rule. Okay. You can put OH in any of the molecule and H in any of the molecule. It's basically the same answer. Okay. So our final answer will be butanol. So this will be the final structure. Now, moving to the next question, we have to determine the enthalpy delta H of combustion for butene using section 11 of the data booklet. Okay, so they also have given us this reaction and we have to use section 11 specifically. So this is section 11. It gives you the bond enthalpies. So which ones do we need? Okay, so which bonds are broken? So I know that 6 O2, all of the O2 bonds will be broken, okay, because there are no O2 on the product side. So 6 OO bonds will be broken. This double bond will be broken, right? So 1 CC bond will be broken. 8 CH bonds will be broken. All of the carbon hydrogen bonds will be broken because there is none of the carbon hydrogen bonds in there on the right hand side. And two of the CC bonds will be broken. That is these bonds. Okay. Like if I write the structure like this, these 2 bonds will be broken. So this is all of the bonds that is broken. And which bonds are formed? So each carbon dioxide molecules will have 2 C double bond C double bond O. Okay. So total of 8 C double bond O and H2O. Each of the H2 OH molecule will have 2 OH bonds. So total of 8 OH bonds for the bonds formed. Okay. Now we have to do summation of total bonds broken. Or summation delta H of the bonds broken. We have to sum up all the enthalpies of these bonds. So we first have O double bond O, we have 6 O double bond O. Okay, so O double bond is 498. So 498 times 6. 1 C double bond C. C double bond C is 614. So plus 14. Then we have 8 of CH and 2 of C double bond C. So here is CC, 2 of CC, and we have CH, right? And this is CH 414. So 8 of 414 and 2 of 346. If you add this, you get 7606 kilojoules. Now we also have to do it the same thing for the bonds formed. So here it's easier because you have just have C double bond O and OH. Enthalpy of OH is 643 and enthalpy of C double bond O is 804. Okay. So we will have 8 times 804 plus 8 times 463, which finally sums up to 10136. Now delta H is basically delta H of this reaction will become bonds broken minus bonds formed. Okay, because breaking of bonds is endothermic while forming of bonds is exothermic. Okay, so bonds broken is 7606. There's a summation of bonds broken. I guess I missed the summation signs. And bonds formed is minus 10136. So the net enthalpy is 2530 kilojoules. But this is the final answer to this question. In the next part, we have to find the hybridization of carbon 1 and carbon 2. Okay, so to find hybridization in organic compounds, I discussed a trick. Okay, in this trick, I told you that every single bond has one sigma bond, every double bond has one sigma and one pi. 1 sigma 1 pi, and every triple bond has 1 sigma and 2 pi bonds. Okay, so using this trick we can actually calculate for the hybridization. So how to calculate it? So the total number of electron pairs around this carbon will be equal to the number of sigma bonds, and using the same hybridization method we can find it. For the first carbon, see there are 3 hydrogens around this carbon. Okay, so 1 sigma 1 sigma 1 sigma 1 sigma, so 4 sigma bonds are around this carbon atom. Okay, 4 sigma bonds means there are 4 electron pairs, as I told you. Okay, 4 electron pair means sp3. The first one will be sp3. Second one, you have sigma sigma and 1 sigma here. You have 3 sigma bonds around this carbon atom. So if you have 3 sigma bonds, your number of electron pairs will again be 3, and your hybridization will become sp2. And that's all about this question. Now we have to draw sigma and pi bonds. Okay, I'll just be using the p orbitals. I mean the p sub. This is a p orbital basically. So what happens here? P orbitals are dumbbell shaped, and if you have this head-on overlap, okay, then it would be a sigma bond. And obviously just also mention the negative and positive signs of the law because this is really important. If you miss this, obviously marks will be deducted. So yeah, so these two positives, when they overlap with each other, a sigma bond is formed, and when there is a side-on or a lateral overlap, what happens is pi bond is formed. Again, you have to see that the overlap should be between positive positive and negative negative. Don't flip it, else what happens is anti-bonding stuff happens. Now mind, we're done with this question. So now in part E, we have to sketch the mechanism of the reaction of 2-methyl-butene with hydrogen bromide. Okay, so this is the 2-methyl-butene. Okay, it's also written here, and HBr. In HBr, hydrogen will be partially positive charge and Br will be partially negative charge. This is because Br is more electronegative as compared to hydrogen. So Br will try to pull electrons towards itself, and hence it will have a little extra negative charge as compared to hydrogens. So Br will have a delta negative charge and hydrogen will have a delta positive charge. Now this double bond is basically highly dense with electrons, and they are looking for a positive center because electrons are negatively charged. When this HBr is close to this double bond, what happens is this double bond will attack this hydrogen and kick out the Br. Okay, as a result, what happens is you can get two specific structure. If the hydrogen is attached to this carbon, okay, you will get structure 1. If the hydrogen is attached to this carbon, you will get structure 2. Okay, so we will have two structures. Now what happens is carbocation 1 is more stable as compared to carbocation 2. Okay, so carbocation 1 will give us the major product. So carbocation 1, this plus Br minus, so you have to just attach the Br on this carbon, and this will give you the final major product. You can also do it for the minor product, but yeah, just writing the final major product will fetch you the full marks. Okay. Now the next question is why the major product is 2-bromo-2-methylbutane and not 2-bromo-3-methylbutane. Now comes the explanation why carbocation 1 is more stable as compared to carbocation 2. Now main thing about major products comes from the carbocation. The carbocation which is more stable will give you the major product of the reaction. Okay. Now why is carbocation 1 more stable than carbocation 2? This is due to the inductive effect. What happens is around this positive charge you have 3 methyl groups around it. I mean 3 methyl groups are surrounding this positive atom. So what happens is these methyl groups, they donate or they push electrons. Okay. This is a minus I group basically. So yeah, they will push electrons and they will try to decrease this positive charge. So there are 3 methyl groups here, but for here you see there are only 2 methyl groups. Okay, so what happens is this charge, it will be decreased, but it won't be as much decreased as in case 1. Okay, because you have 3 methyl groups trying to push electrons. So charge will be less for carbocation 1 as compared to carbocation 2. And we know lesser charge means higher stability. So that's the reason carbocation 1 is more stable. So yeah, that's why 2-bromo-2-methylbutane is the major product. I've just written that it happened because electron donating effect of CH3 group. Positive charge in carbocation 1 is surrounded by 3 alkyl groups as compared to 2 in carbocation 2. Hence it's more stable. So that's all basically. Now moving on to part G. Combustion analysis of an unknown organic compound indicated that it contained carbon, hydrogen, and oxygen. So we have the mass spectrum basically, and we need to identify two features. One from M by Z 7058 and M by Z 43. What is M by Z 58? 58C is the last peak. Okay, and we know that the last peak gives you the molar mass of the compound. Okay, so the molar mass of the compound is equal to 58, and we have to calculate and also find out. Do an analysis of M by Z 43. What exactly happened between them? So what happened is you see that the mass difference between them is 15. Okay, so if the mass difference is 15, we can say that the methyl group was removed from the compound. Okay, we have to use section 28 of the data booklet. See, mass loss 15 means we have lost a CH3 or the methyl group. That's all about the part 1 of G. Now we can go here. That is a part 2. There's an infrared spectrum. So we have to find the data booklet, and Yeah, basically we have to identify which bond is responsible for this absorption at E, or you have to find why. Which bond is responsible for this big dip. Okay, so how to exactly do it? Like identify the fingerprint region that is like above 1500, and then try to estimate what can be this value. I can say that this value is around 1700-ish. Okay, so now let's get to section 26. Okay, around 1700 to 1715 we have the C double bond, that is aldehyde ketone carboxylic acid esters. Okay, and I can say this is a little more than 1700 too. So 1700 to 1750, that holds correct. So there is a C double bond, but I don't know which C double bond. I just know that it's a C double bond. Anything can be aldehyde, ketone, carboxylic acid, or esters. Now we have to identify the unknown compound using the previous information and this HNMR spectrum and section 27. Okay, so here you see there is only one peak, and this is a huge peak. Okay, so if there is one peak, then you can say that this compound is kind of symmetrical. Okay, and there are no other hydrogen other than one that is exactly beside the C double bond group. Okay, because if someone has C double bond, I'm expecting something like this. Okay, something like this. It's just a complete expectation. So yeah, this molecule is symmetrical. That is one information. And from this and one peak, we can say that C double bond O is surrounded by two alkyl groups on both sides. Okay, so let's start by putting the alkyl groups as methyl groups. And if we put them as methyl groups, we see that our molar mass matches. Okay, and that's why this is our final compound. Okay, now if this, if the molar masses didn't match, then we have to change the alkyl groups. Okay, maybe put two ethyl groups and then two the next one propyl groups, etc. But yeah, from this peak, which is around from 2 something greater than 2, we can clearly say that this is kind of a ketone group. Okay, so that's all about this question. The next one is we have to draw the stereoisomers of butyl toll using wedge and dash representation. So this will be your stereoisomers. This is the first isomer. The second isomer will be you can say a mirror image of this one. So you will end up with this structure. The last question here is we have to outline how two enantiomers can be distinguished using a polarimeter. So what happens is enantiomers can rotate the plane of a polarized light. Okay, so two enantiomers will rotate the plane of the polarized light by equal amounts but in opposite direction. Okay, so enantiomer 1 will maybe rotate the light by plus 17 degree and enantiomer 2 will rotate the light by minus 17 degree. That's all about question 4. Let's move on to question 5. So we have ethanol and methanoic acid. They are important industrial products. Ethanol is used as a fuel. So we have to write the chemical equation of the complete combustion of ethanol. So this is it's pretty easy. It's just a combustion reaction. Ethanol with CO2 will give you CO2 and H2. Then we have to balance it. Upon balancing, we see that there will be a 3 in front of O2, 2 in front of carbon, and 3 in front of hydrogen. The next part, we have to reduce the enthalpy when 56 grams of ethanol is burned. Okay, and we have to use the section 13 of the data booklet. So 56 grams, firstly, let's try to find the moles. Molar mass of ethanol is 46, so 56 divided by 46 will give us the mole, that is 1.217. Okay, now the total enthalpy will be this moles times the enthalpy of combustion of ethanol, and that we will get from section 13. So upon coming to section 13, you see you will get the enthalpy of combustion values. So find ethanol here in liquid state. So you will get minus 1367. So 1.217 times minus 1367 will give you this value, that is minus 1663.64 kilojoules. That is the final and the total enthalpy value. Now, oxidation of ethanol with potassium dichromate can form two different products. Determine the name of the organic products and the methods used to isolate them. Okay, so ethanol, if you oxidize ethanol, it will produce an aldehyde ethanol. Okay, if you further oxidize it, it will form ethanoic acid. So ethanol and ethanoic acid are the two other organic products that will be formed. Two organic products that will be formed after oxidation of ethanol. Now, how can we separate them? For ethanol, we can just use distillation. For ethanoic acid, we can reflux after distillation. Okay, so you can just use this distillation, then reflux the rest of the solution. You will end up with ethanoic acid. Now, the next question, write the equation and name of organic compound where ethanol reacts with ethanoic acid. So an alcohol and acid react to form an ester. Okay, and that's what exactly is shown here. This is your alcohol, this is your acid. So finally, you will get HCOO, CH2CH3 plus H2O. And you have to obviously place H plus here because you have to put some drops of some concentrated acid. And the product is ethyl methanoate. Okay, that's the standard way of writing the name of an ester. Write this part first and then the acid part. We have to draw the titration curve with methanoic acid and sodium hydroxide. So, and we should also show how to determine the pKa value. So methanoic acid is a weak acid while sodium hydroxide is a strong base. Okay, what happens is initially, at the end of the reaction, the pH will be greater than 7 or it will be basic. As NaOH is a strong base, it will be much basic. Okay, so I can say that the end pH will be here. In the beginning, as methanoic acid is a weak acid, it's an acid, right? So our pH will start at a value less than 7. Now, as it is a weak acid, strong base titration, at 7, the curve will increase very steeply. Okay, so we can somehow find the volume at equivalence. Okay, that is the volume when the pH exactly becomes 7, and half we have to find out half of this volume. Okay, so if this volume is 35, we have to go to 17.5. The value of pH at half of the equivalence volume will give you the pKa. Okay, so again we have to find the volume at equivalence. Half of this volume of equivalence will give you the pKa value. Okay, and that's how we calculate the pKa. Now, which indicator can be used using section 22? So indicator, like obviously NaOH is a strong base, so anything that is greater than 7 can be used. So here, it should be a little greater than 7. I would suggest if you take up something greater than 8. Okay, so we have two indicators here, phenol red and phenolphthalein. Any of these two will work. Okay, I have chosen phenol red because it's at kind of at the best levels of 6.8 to 8.4. But even if you write phenolphthalein, that's the correct answer. Now, starting with question number 6. In question number 6, bromate and bromide ions react in acidic aqueous solutions. There is a balanced chemical reaction, and there is the rate data. We have to determine the rate expression for the following reactions. So, firstly, we have to identify the order of reactions, and then with this, we have to calculate the rate expression. In the first case, see, these are the initial concentration, and this is the initial rate. Okay, so we are doubling the BrO3 minus concentration, keeping Br minus and H plus constant. Okay, while doubling this BrO3 minus concentration, you see that the initial rate also got doubled. Okay, so that means the rate is directly proportional to BrO3 minus concentration. So the order of reaction with respect to BrO3 is -1. In this, similarly, we keep the BrO3 minus concentration constant and double the Br minus concentration. We see that our initial rate also gets doubled. So our order of reaction with respect to Br minus is also 1. Now again coming back to step 1. Okay, this is 0.1, this is 0.1. Now we are doubling the H plus concentration. We see that the initial rate is becoming 4 times. Okay, this means that the order with respect to H plus is 2. If you are doubling H plus, our rate increases by 4 times. The order with respect to H plus is 2. So the final rate becomes K BrO3 minus Br minus and H plus whole square. There's a final rate expression. You have to find the value and unit of the rate constant using rate expression A. So we know that the unit of rate is mole dm cube per second. Okay, we need to find the unit of K, and we know that the unit of concentration is mole per dm cube. So for BrO3 minus mole per dm cube, Br minus mole per dm cube, H plus whole square, it will be mole per dm cube whole square. So we need to find the unit of this. Upon solving, we get the unit as dm to the power of 9 mole cube second. This is the unit of K. Now what happens is we have to find the value of K. So let's go to the initial value. Okay, so we have the Br minus concentration, we have the BrO3 minus concentration, we have the H plus concentration. Just plug them in this equation and find the value of K. This is the initial rate. Initial rate is 8 times 10 to the power minus 4. This is K. This is 0.1, 0.1, 0.1 whole square. So this is K times 10 to the power minus 4. Upon solving, we get K as 8 dm to the power of 9 mole cube second. And that's the answer to this question. Moving on to part 7. We have the following equilibrium reaction. Twice SO2 plus O2 gives you twice SO3. We have to find the equilibrium constant Kc. Kc will be again like using the normal laws to write the equilibrium constant. For like on the numerator we have the products, and on the denominator we have the reactant. So SO3 whole square, these stoichiometric coefficient goes in the powers. So yeah, so SO3 whole square divided by SO2 whole square times O2. That's the equilibrium constant. Now we have to explain what happens on increasing the volume of the container at a constant temperature. Okay, what happens if temperature is constant? On increasing the volume, pressure decreases. Okay, we have the relation PV equals nRT. Okay, if temperature is constant, PV is constant. Okay, if PV is constant, what we can say is P is directly proportional to 1 by V. Okay, if we increase the volume, our pressure will decrease. They're inversely proportional to each other. Okay, so now by Last-Hartley principle, if the pressure decreases, what happens is the reaction shift to the side having greater moles of gas. Okay, because what happens is if pressure increases, we need more moles of gas to increase the pressure. Last-Hartley principle says any change, the system will try to resist any change. So if you're decreasing pressure, you'll try to make more gaseous moles and increase the pressure of the system. Okay, here you see the gaseous moles is more of the gaseous moles is on the left side. So the reaction will shift to the left, and so equilibrium shifts to the reactant side. That's the answer to this question. Now there's probably the last question here. So SO2, O2 and SO3 are mixed and allowed to reach equilibrium at 600 degrees Celsius. We have to determine the value of Kc at 600 degrees Celsius. So we have the initial concentration and the equilibrium concentration of SO2 is given. So how many moles of SO2 has been reacted? 0.5. Okay, the difference between these two. Now how many moles of O2 reacted? So we have to use stoichiometry here, SO2 and O2. So moles of O2 by moles of SO2. This is reacted. Okay, this will be equal to half. So moles of O2 will be moles of O2 reacted. Okay, will be moles of SO2 reacted by 2. So moles of SO2 reacted is 0.5. So moles of O2 reacted will be 0.5 divided by 2, that is 0.25. The moles of O2 left is 1.5 minus 0.25, that this will be 1.25 basically. And moles of SO3. Now stoichiometries of SO2 and SO3 are same. So if 0.5 moles of SO3 are reacted, so 0.5 moles of if 0.5 moles of SO2 have been reacted, so what happens is 0.5 moles of SO3 will be formed. Okay, so moles of SO3 formed, that is 0.5. In this case, SO3 is getting formed, so we have to add 3 plus 0.5, that is 3.5. Okay. So that's it. We have got the moles. Let's just assume that the total volume of the mixture is, total volume of the container is 1. So these terms will become eventually become the concentrations. Okay, moles divided by concentration, or moles divided by volume. Volume is 1. Now Kc will be SO3 whole square divided by SO2 whole square times O2. Plug in the values 3.5, 1.5, 1.5 whole square times 1.25. We get 4.36, which is the final answer to this question. With this, we come to the end of this paper. If you like this video, do subscribe to my channel. I will soon be posting the solutions of paper 1. Thank you so much. Have a nice day.